Okay. Take two. So today, if I can get control of the class back, we're finally going to do Fibonacci numbers and generating functions. Okay? So, if you have not seen the Fibonacci numbers before, the door is over there. You're welcome to leave. This is almost a prerequisite to be, this far in mathematics. Okay? You've at least seen them, if no other place, than how to email me anonymously if you have any concerns about this class, Williams, or life and death. There are lots of ways to define them. For us, I'm going to use the standard definition. F0 is 0, F1 is 1, Fn plus 2 is Fn plus 1 plus Fn. If you do some research with me, you'll see a slightly different definition, which is actually more useful for some things. So the question is, how do we figure out what the nth Fibonacci number is? Well, I've given you all the information. You can just go iteratively down the line and calculate them. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and you can just keep going. Now, if you want to calculate the millionth Fibonacci number, this is not pleasant. So the question is there a nice way to get the Fibonacci numbers? If you watched the video, which I know you all have, it talks about an application of a sequence related to the Fibonacci numbers, and how you can use this to analyze certain strategies in roulette, and why you should not play roulette with the double plus one strategy. So how can I jump to the nth? Well, it turns out there's a beautiful formula called Benet's formula. The nth Fibonacci number is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 plus root 5 over 2 to the n, minus. Okay. Now what's nice is this number in absolute value is less than 1. So when n is really large, this number is essentially 0. The nth Fibonacci number is essentially this, and what this tells us is it's the closest integer. So just calculate the closest integer to this, and you found your nth Fibonacci number. Now again, we've talked several times that this does not look like an integer. If you see this in a police lineup and you have to identify the integer, this should not be getting initial votes. It has division by 2, it has square root of 5. Everything cancels. As a nice problem, investigate what integers can you replace 2 and 5 by so that this is always an integer. How often will this be an integer? For what pairs of integers does this always take on integral values? And what's the relationship between the two choices? One way to prove this is the method of divine inspiration. I believe this is the nth Fibonacci number. All I have to do is show that this is the nth Fibonacci number. How do I do this? I show when n equals 0, I get 0. When n equals 1, I get 1. And then I show that this number satisfies the recurrence relation. The recurrence relation uniquely determines the Fibonacci's once you know the initial conditions. I think there are 2 people at most. Wait, no, that was too complex analysis. Has anybody here taken differential equations? Oh, even better than complex 3.5. Okay, so if you've taken differential equations, if you know the initial conditions, that describes uniquely how the system evolves in time. Over here, I need 2 initial conditions. Why do I need 2 initial conditions for the Fibonacci's? I'm using
3 numbers are the 2 previous.
I'm using the 2 previous, right? So you now have at least another M&M in the bank.
Well, I think I stocked up.
Okay. If I had a 3-term recurrence relation, if I had plus Fn minus 1, I would need another piece of initial information to uniquely specify it. Okay. The method of divine inspiration, while powerful, you cannot always count on it working. So what I want to do is I want to show you how you can get the Fibonacci numbers through generating functions. And this is a great way to motivate why we care about generating functions. What are we going to be choosing our coefficients of generating functions later in the semester? What are they going to be in our class? Yes? Probabilities, right? And in fact, one of the generating functions that we're going to see is called the probability generating function, to really drive home the point. Another one we're going to study is the moment generating function, which is a close cousin of the probability generating function, and you can figure out, I hope, what it's useful for studying. Okay, so was that the battery or was that someone's phone? Was that someone's phone? Okay. All right, so let's define GF of x to be the sum, and goes from 0 to infinity, Fn x to the n. So this is the generating function associated to the Fibonacci's. Think of it as a Taylor series expansion. Now, the first question you should have is, does this converge? And so I can trivially prove it converges for some x's. This is probably not in the book. This is a good thing to do whenever you see something doesn't converge. Can anybody give me a growth rate for the Fibonaccis? I want a sequence that grows faster than the Fibonaccis. 2 to the n. Excellent. Why 2 to the n?
Wasn't that intractable?
You're close. Why 2 to the n?
Because each time it less than doubles.
It less than doubles.
Yeah.
If I replaced fn with fn plus 1, then each term would be twice the previous. But since it's not, it's going to go slower. So since fn is less than or equal to 2 to the n, it will converge if the absolute value of x is less than what? So this is growing at most 2 to the n. If x is less than what will it converge? 1/2. Good. So at least it makes sense to talk about this function. And of course, x can be a little bit larger than 1/2. It can go up to 1 over essentially the golden mean. Okay, so the function at least makes sense. The problem is if you look at this, it doesn't really look that useful. I don't really know what the Fibonacci numbers is, so forming a function whose coefficients are the numbers I'm trying to find doesn't really seem like the greatest idea. The reason it is a great idea is you know the Fibonacci numbers, you just don't know that you know them. Okay? You know them. Once you know the initial conditions and the recurrence relation, everything else is uniquely determined. So the sequence is uniquely determined. You can deduce any Fibonacci number you want. The question is, how can we use this now to extract something useful? So this idea of pulling something out, culling something from generating functions is extremely powerful. So let's look at it a little bit more carefully. GF of x is going to be the sum, and I'm going to start from n equals 2. And I'm going to write it as Fn, and so I'm going to just carefully play some games. Okay, so what I really want to do is I want to start my sum at n equals 2 because I want to then use the Fibonacci recurrence. But the initial sum starts at 0. So my first term here now is f2x2. So which term am I missing? I'm missing f1x plus f0 times 1. Is it really bad that I'm missing f0 times 1? No, it's just 0. What about f1 times x?
It's just x.
It's just x, but I do have to be careful to keep that. Okay, so now what comes next? I have the sum, n goes from 0 to infinity. Fn plus 2 is just Fn plus 1 plus Fn times x to the n plus 2 plus x. And so now if I write this, I have the sum, n goes from 0 to infinity, Fn plus 1, xn plus 2, plus the sum, n goes from 0 to infinity, Fn x to the n plus 2 plus x. This function almost looks like gf of x. What's the only difference between this and gf of x? Yes?
Just multiplied by an x squared.
I've just multiplied by an x squared. If I take away the extra x squared, that's just my function gf. So I can pull out an x squared, advantage of being on the board, and that's just my gf of x. What about this function? Yes?
GF of x from 1 to infinity multiplied by x.
Good, it's gf of x from 1 to infinity multiplied by x. Fortunately, that's the same as gf of x because the 0th coefficient is 0. So here I would pull out just an x, and so I get x gf of x plus x squared gf of x plus x. Okay? So I'm just doing some algebra, yes?
Sorry, from the first line, why did we start with f of n plus 2?
I just wanted to rewrite it like this to simplify using the recurrence relation. I want to replace the Fibonacci numbers with the sum of the two previous.
And then why are we adding on F1?
Well, because over here, notice my first term is going to be f2x squared, then f3x cubed, and f4x to the fourth.
Oh, you have to add
I'm
this.
missing f0, x to the 0, f1, x to the 1.
Okay.
So I have to add on those two terms
To make it equal to the...
to make it equal to what I start with.
Okay.
If you've taken differential equations, this is very similar to series expansions.
So for f of n plus 1 in the third line,
Yes.
replace that with gf of x since f is 0.
Exactly. Yes. So over here, this is using f0 equals 0. Otherwise, it's really gf of x minus f0.
Okay.
But because f0 is just 0, okay, what do we do now?
Solve for gf.
Yeah, we solve for gf of x. Gf of x minus x g of s minus x squared gf of x is equal to x. Therefore, gf of x is equal to x over 1 minus x squared. Absolutely amazing. We have a closed form expression for gf of x. And this is just the sum, n goes from 0 to infinity, of fn x to the n. So if we can expand this out, we can actually just pluck off the Fibonacci coefficients one after the other. Now when you took calculus, what was your least favorite integration method?
Partial fractions.
Yeah, usually partial fractions is at the top of the list, right? This is one of the places where partial fractions is extremely useful. When you see something like this, there's two ways to think about the denominator. You could try to expand it by calling this whole thing down here the ratio r, and write it as 1 minus quantity x plus x squared. The problem is if you try to do that when you expand, you're going to have terms of different degrees. So if you try to write it as 1 over 1 minus x plus x squared, that would be 1 plus x squared plus x squared squared. Ugh. This has an x squared term, and this has an x squared term. This would become a nightmare to try to expand. So you don't want to do this. What you want to do is you want to do partial fractions. You write 1 over 1 minus x squared as 1 over 1 minus alpha x, 1 minus beta x. So you factor the denominator. And if you think about it, if you steer it, this is very closely related to the Fibonacci recurrence relation of the golden mean. Yes?
One of them be positive, or beta, or
Okay. Yeah, so one of them is going to be positive, one of them will be negative, and they'll be related to the golden mean and the reciprocal of the golden mean. And so I will let you have the fun of factoring this and seeing the Fibonacci's golden mean come out. And now, you write this in terms of partial fractions, and so you can write x over 1 minus x squared as a over 1 minus alpha x plus b over 1 minus beta x. I'm not going to go through the algebra on the board for two reasons. One, it's in the book, and odds are I would make a mistake. Okay? You don't want to see me do algebra in public, okay? You really don't. You don't want class time spent on that. This is something you can read. This is something even better for you to do at home. You want to get a sense of, will this work? This is just a partial fraction decomposition. And now I can use the geometric series for each one of these very nicely. And I'll get the sum, n goes from 0 to infinity, a times alpha to the n plus b times beta to the n, x to the n. And that's just the same as the sum, n goes from 0 to infinity, of fn x to the n. So these must be equal. And this gives you a way to find the Fibonacci numbers. Okay? So any questions about how we can use generating functions to find the Fibonacci's? So again, strongly urge you to do the algebra, but we showed before that these are unique, that if these two series are the same, we can pluck off the terms one at a time. Take x equals 0, then divide by x, take x equals 0 again, or differentiate. We can actually differentiate term by term because these series converge. And so if these two series are the same, they have to be the same term by term.
But this is only for discrete cases.
Right. But again, right now, I have two different infinite series. If two infinite series are the same, the infinite series will be the same term by term. The difference is I could have two random variables that have the same associated sequences without the same associated generating functions without being the same. But if I give you two series expansions that are the same, the only way they can be the same is if they're the same term by term. If not, there'll be some first term where they're different. Look at a very small x near 0, and you will see a difference. Okay, so this is absolutely amazing. This allows us to get the Fibonacci numbers in closed form. And in fact, you can do this for any recurrence relation. It all comes down to how well can you solve polynomials. If it's a quadratic, it's not a problem. If it's a cubic or quartic, it's a pain, but there are formulas. In general, however, you're stuck and you have to numerically approximate roots, or you just have to say, I'll call the roots R1, R2, R3, and so on. I want to give one more application of generating functions before we shift gears to probability generating functions. And I think we've done this problem already in the semester. What is the sum, n goes from 0 to n, of n choose m squared? Does anybody remember the answer to this? I think we did this earlier in the semester. That's a very skeptical look. We might not have. It's 2n choose n. And the way to look at this is n choose m squared is n choose m, n choose n minus m. Think of it as you have n people from Williams, and you have n people, I won't do it, I'll do my alma mater, I'll do Yale. Okay? And I want to form a group of n people.
N people from Yale? You made n both of them?
Yes.
Okay.
Yes. So I have 2n people. I want a group of n. How many ways can I have a group of n people from 2n people? 2n choose n. The other way to look at it is, if I'm forming a group, I have to choose some number of people from Williams. Let's let m be the number of people I choose from Williams. Well, if I choose m from Williams, how many do I have to choose from Yale? n minus m. And then I just sum over all possible values of m. And so then that also has to be 2n choose n. So this is a way to prove this binomial identity. The difficulty is you have to figure out what's the right story to tell. Okay? And so if you happen to think of the story, it's a nice proof, but what if I give you something slightly different? So what I want to do is I want to show you how you can use generating functions to solve a problem like this. And then there's a nice application of the method I'm about to show you. Okay, so generating functions. So let's let g of s be the sum, m goes from 0 to n, of n choose m, s to the m. Okay? And now what I can do is I can look at g of s times g of s. Can someone tell me first of all what g of s equals? Can you simplify g of s? So what does that sum equal?
S plus 1 to the m.
Yes. Either s plus 1 to the m or 1 plus s to the m. Either way. So I can write this as the sum n goes from 0 to infinity of n choose m, s to the m, 1 to the n minus m. And if I write it like that, it now looks like the binomial. And so this would just be s plus 1 to the m. Okay, so what can you tell me about g of s times g of s? Well, that's got to be s plus 1 to the n. Oh, sorry, this is to the n. That's got to be s plus 1 to the n. S plus 1 to the n. Can anybody simplify? S plus 1 to the 2n. So this is then the sum, k goes from 0 to 2n, of 2n choose k, s to the k. And now we're almost done. We've talked about what happens when I multiply generating functions. If I have, two independent random variables, the product of the generating functions is essentially going to be the generating function of their sum. And that's basically what I have here. So if I want to look at how do I get the middle term, the s to the n term, the s to the n term. If I look at it from s plus 1 to the 2n, it is just 2n choose n. Right? And if I look at it from here, if I take gs times g of s, so I'll have maybe the sum m1 goes from 0 to n of n choose m1 s to the m1 times the sum m2 goes from 0 to n choose m2 s to the m2. How would I get a term where s is to the power n? Well, whatever power this is, if this is to the mth power, this would have to be to the n minus mth power. So, nth power of s is just going to be the sum, m goes from 0 to n choose m, n choose n minus m, the s to the n. So they have to be equal. So the only way this can equal that is if 2n choose n is the sum over here. So we see that 2n choose n is the sum, n goes from 0 to n choose m, n choose n minus m. Okay, we're probably not going to have time to cover it in the semester. It's one of the extra chapters in the book. It might even be in the killed section of the book. It's on sequences of runs of heads. So if I flip a coin, and the coin doesn't necessarily have to be fair, how many alterations do I expect to get between heads and tails? How long do I expect the longest run to be? When you're looking at how many runs there are, ideas like this are extremely important in terms of allowing you to analyze how many altercations do we have between heads and tails. This is one of the best ways for professors to make money from students in probability class. What's the other good way? Yes? Birthday problem. Birthday problem is probably the easiest. This is probably the second easiest, is generate a random sequence of 100 heads and tails. That's fine. Anybody who wants to get an M&M during class is welcome to do so. If you want, I'll even start strategically positioning M&Ms throughout the class. Okay? The goal is for class participation. It's worth the cost. If people are trying to figure out, is a sequence random or not, a really good test is how many heads, how many tails. If it's a fair coin, we expect about 50-50. The next thing is the length of the run, or how many runs we have, how many alterations between heads and tails. And so using ideas like this, it becomes very easy to analyze. Okay. If you happen to see the battery stop, let me know. Even though it's charged, it's now gone down to absolutely no battery. So, okay. So this is the basics of generating functions. Now this is a class on probability, so we want to do things on probability generating functions. So, probability generating function. And so we'll say that the generating function of a random variable x is just the sum of s to the xm, and then the probability that x equals xm. or it could be the integral of s to the x in the density function. You know, we could have the continuous or we could have the discrete. Okay, now if we want to analyze this, if you want to analyze the sum, it's really nice if xm only takes on non-negative integer values. What would be annoying if x could range over all the integers? So look, what happened if maybe xm goes from minus infinity to infinity? What would be difficult to study? The difficulty of xm. So what would be challenging?
Seeing if they converge.
I'm sorry?
Seeing whether it converges.
Yes, so why would we have some convergence issues?
Because if s is less than 1, then it's probably going to be good if x is always positive, but if x ends up being negative, then that'll make that term be bigger than 1.
Good. So, I mean, the probabilities are always at most 1. But if s is less than 1, if we have it to a negative power, we made it larger. So we could have some issues with things being blown up too fast. There's so maybe issue if absolute value of s is less than 1. Because otherwise, this will clearly converge if the xm's only take on non-negative integer values. This will clearly converge because all these probabilities are at most 1, and they'll be bounded by a geometric series. There's another more basic problem. If I give you a Taylor series, what's your favorite point to evaluate it at?
0.
Right. What's the only point where you can't impress me by knowing the value of a Taylor series?
0.
0, right? The Taylor series has to converge to the original function at 0. It's not that impressive to say, look, Professor, it agrees. Well, yes, you wrote your Taylor series as f of 0 plus some multiple of x, and when you plug in x equals 0, the multiple of x vanishes, and you just get back the value of your function. I'm not that impressed. Right? X equals 0, that's our basic point to study things. What's the basic point to study a generating function at? Where would you want to study the generating function? What's the simplest value s to choose? 0. And if you have negative if you have negative values now, we have 0 to a negative power. Can't evaluate at s equals 0. Okay. So there's a lot of issues if we allow negative values. Now, there are some random variables that are allowed to be negative. Not everything has to be positive. If you think about nice events like, I don't know, number of car accidents, right, in an intersection, that's a nice event. It's not going to be negative. It'll be integer valued. That'll be something very good for something like this. If you think about a stock price movement, however, that unfortunately can be negative. And so you have to be a little bit more careful. So fortunately, there's a lot of times when we can get by and just assume that our random variables are non-negative integers. But we do have to be careful for the more general case. Okay. Any questions on the definition of a probability generating function? And then we have a very nice fact. x1, x2, ... xn are independent. Then the generating function of their sum is the product of their generating functions. And this is one of the reasons we really like generating functions. Now, we only proved this when we had sums of 2 generating functions.